ticking down or something, I don't know. Exactly, yeah.
No, what is it now?
Physics!
Basic.
Physics.
What are we doing today?
Yes, tutorial, because we're finished. So, let's see, which ones do we have to do homework on? This one had no questions. These two had questions, didn't they? Yeah. Yeah, we'll start with photons. Please, you'll need your calculator. You're in this room for chemistry, aren't you? Oh, that's on the timetable.
Yes, we're good.
No.
So it's okay if I go over a little bit.
No, a little bit too much.
Yeah, it could take like half an
Half
hour.
an hour. No, 40 minutes. No, we got 10 minutes break in between we have double physics.
Alright, what's the first question here? Mine is slowly opening. What's the first question here in the photons homework? Do you have the questions? Did you try them?
There's photons?
I'm not bring there.
We have one formula.
Yeah, just the one formula. Right, okay. An electron released from a metal surface with that speed. When that wavelength is shone onto it, what is the value of the work function? So we have the one formula for this lesson, which is HF equals KE plus the work function. Now, do we know...
That's the last one after that.
Oh, I'm so sorry.
It's E equals
Wait, this is the...
Oh, we didn't do this homework either.
Yeah,
This was before we took the...
quantum. This is the photon.
This is another one.
This is the lesson of photon. This is the one from that formula, isn't it?
Yeah.
And
Yeah.
photons was before quantum.
And then we do quantum after this.
Yes, and quantum has that formula.
For photon test.
I thought photons had
No,
this
that's
formula.
photons.
Photons is this
This is
formula.
I
The last
thought
lesson
only
we
have
did
Okay,
the...
yes. Okay.
Don't you freaking me out, guys.
Last lesson.
Or maybe not. Maybe this is just... Maybe you're right. I'm so sorry, Yusuf. Maybe this is just the one with the HF in it.
Yeah.
Oh no, wait. No, there it is.
Yeah.
There it is.
There it is. Work function. There we go. All right. Yeah, sorry. You are lose. Okay. An electron released from a metal surface with that speed and that wavelength. Right. So, because we're dealing with wavelength, we'll have to use this formula. Actually, you know what? We might as well just put in the formula for kinetic energy. So the work function is hc over lambda minus a half mv squared. Yes? Are you going to type that in for me, Flan? Let me just write down the info. The only info that you really need is the lambda equals 600 nano. And the V equals 154471. My calculator's still loading. Are you using your phone to calculate it, or are you tweeting, man, I'm doing an awesome physics question right now. So rad. Hashtag physics. What? M. Oh, massive electron. Shit.
No,
Is that -9 or a 9? Or
Number
4?
three. Number 3.
ME?
There, yeah. What?
-9.
-9, yeah.
Huh?
And do I want it in electron volts? I'm sure I do. Now give it to me in electron volts.
Yay.
2.068 electron volts. Right, on to number 2 now. Wait, okay, I'll wait.
First exam.
Since you were so helpful with the calculator.
We have a day off before our math exam. Are we gonna do revision on that day or not?
I'll still be in school, it's a weekday. So if you want to I mean, practically all the rooms will be empty, except for the ones being used for the test. So we could totally do this. It is not a problem.
And the day before we have English.
The day before what?
We have English.
When?
EAP.
The day before math?
Like Wednesday, Thursday. Wednesday we have EAP. And then Thursday we have, and then Friday.
So if we were really desperate, you could do a class on Wednesday too.
We are really desperate.
Then class on Wednesday it is. Right, number 2. The photosystem of an organic life form is, now this question is not biologically accurate. The photosystem of organic life form is made up of magnesium with a work function of 3.68 electron volts. A photon of UV light from the sun hits the metal surface. I was actually talking to the biology teacher about this photosynthesis process, and actually I was surprised to learn that the photosynthesis process is based off of this physics idea that the magnesium that's in our cells, plant cells rather, magnesium that's in plant cells is a metal. Magnesium is a metal, and it means that when light from the sun hits it, an electron is released. And this electron
yes,
is...
you didn't know this.
Huh?
You didn't know this.
I didn't study biology.
Oh.
I only studied biology to a baby school level, like, cells, DNA, anyways, the free electron is what basically has the energy. However, I discovered that in real life, the energy from the photon is not enough to release the electron from the magnesium. So the cell has this sort of special system where it can use to collect up the energy from the photons until enough is available to release the electron from the stores it, until it can release it. So anyways, that's just an interesting biology aside. So I've simplified this question because a photon by itself cannot free it. Anyways, what have we got here? How much kinetic energy does the freed electron have? Well, again, we're using this formula, except this time we're looking at kinetic energy. So kinetic energy would equal HF minus work function, which is HC over lambda minus work function, which is HC over lambda, which is... Come on. Oh, for goodness sake, what's happened to you? No! Something terrible's gone wrong. Oh no, it's okay. 300 nano and 3.68. Now, because that's electron volts, we'll have to put an E in here. Alright, allow me. What constant number is H, please? 17? 6, is it right? And C? Thank you.
So we just multiply the workforce by E.
Yeah, because we want it in joules.
We can't multiply the whole amount.
No, just this part here. I got a tiny 7.25 times 10 to the minus 20 joules. Okie dokes. Yep. What is the threshold frequency? Do you remember the formula for threshold frequency? It's equal to, oh my goodness, I've forgotten it. H over work function, isn't it? Or it's work function over H?
Over P.
No. H over work function over H. No, the threshold frequency.
Oh, it's work function over H. Lambda equals the H over momentum.
No, it's work function over H.
Like this?
Yeah. Yes.
Right. Once again, for all time's sake, what is it? 7 for the H constant?
6.
6. 8.898 times 10 to the 14 hertz. Finally, what is the maximum wavelength of light that will free an electron? So remember, I'm being a bit sneaky here, this is the minimum frequency to free the electron. And if you think about the formula, wavelength equals c over frequency. When the frequency is at its minimum, the wavelength is at its maximum because of the 1 over relationship. So this is just a fancy way of me saying what's the wavelength here, the threshold wavelength, which will be c over the threshold frequency. That comes in at, let's do it in nanos. 337 nanometers. Now, the reason I was sneaky there like that is because they were sneaky 1 year in the same way. Okay? Number 3. A 10 centimeter by 10 centimeter photocell is made of copper with a work function of 5 electron volts, light of wavelength 650 nanometers, and intensity of 120 watts per square meter is shone onto the photocell. How much energy per second does the plate receive from the light? So, can anyone see per second how much energy this photocell is getting, this solar panel? And I'll give you a clue. You need to be focusing on this.
120
Yeah.
over 5 times 1.6?
No.
Hour is work over time.
Yes.
120 over the area.
Getting closer, but not that.
Area over.
Close. Well, think about what this is saying. It's saying per second, it's 120 joules
Per meter.
per meter squared.
Yeah.
We want the hour?
We want the energy in a second that falls on this. So if 120 joules per second per meter square fall on this, then 12 joules per second per meter square fall on this, because this is 1/10 of a meter squared.
Again?
This area is 1/10 of a meter squared. 10 by
Yes,
10.
yes.
So it's 1/10 of 120.
So we multiply.
Multiply by 1 over the area. I'd like as a fraction. Huh? Yeah, just to be clear, if you want to be clear about it, it was 120 times this area in meters though, so that was 0.1 meter squared over 1 meter squared, because it was 120 for 1 meter squared, but you only want a fraction of it.
Why 0.1?
10 times 10 divided by 100.
Is this not 0.1 of a meter squared? Or have I screwed that up?
0.01.
Oh my goodness, that is disgusting. Apologies. 0.01, so 1.2. Now we're
centimeters, 0.1 meters, yes.
0.01.
0.1 times 0.1.
0.1. 10
No,
centimeters.
no, not a hibibi for me, please. All right. If we're calling each other nicknames, I can be Habibi and you can be Gabi. How does that sound?
So why?
So it's 1.2.
10 centimeters.
Dude, new flash. I have one.
Divide by 100 squared because it's a...
Well,
Yes.
Tamam?
thank you.
Great. Continuing then. Now, that was part A. B. Let's see. So how many photons hit the metal surface per second? Well, remember energy equals HF, but when you have many photons, it's NHF. And we want to know what the N is. So the N is 1.2 over HF. Now we don't know the F, do we? No, we only know the wavelength. So that's 1.2 over HC over lambda. So that's 1.2 lambda over hc. It's going to be a pretty big number. Let's see what we get. What number is C? 28, is it?
Yes.
Super. And of course I typed it in backwards. Okay. And what was the wavelength here? 650. Nano. Right, I got 3.927 times 10 to the 18 photons per second. Photons per second. Right, next, how many electrons are freed per second? Okay. Well, let's see. What was the energy of one photon? That's HF. And then what was the 650? Okay, and I'm going to put this in electron volts. So the energy for one photon is 1.907 electron volts. So the answer here is 0. Why are no electrons freed? Look at how many photons are hitting this metal plate. Loads of photons hitting the metal plate. Why are none of the electrons freed?
The frequency of the light is not high enough.
Yeah, the energy of each photon is nearly 2 electron volts. However, the work function is 5 electron volts. None of the photons can free any of the electrons. The answer is 0. So that means for part D, the current is 0 as well. There is no flow of electrons, so there's no current. More interestingly is part E. If I replace the copper with a material which I made up, stevinium, with a low work function of 1 electron volt, what is the current now?
What was the thingy that we found? The energy that we found? 1.9?
Yeah, so now it's definitely enough.
Yeah.
So it now means that each of my photons will have enough energy to free the electron. Not only that, it will have a little bit extra. Where does this extra energy go?
Light.
Light? No.
Speed.
Yeah, kinetic energy of the freed electron. So the kinetic energy of the free electron is equal to 0.907 electron volts. The extra energy went into giving it kinetic energy when freed.
No energy is lost?
In real life, of course, there is, but... Well, no, not for stevinium. It's 100% efficient.
And
Order yours now.
the number of electrons produced is equal to the number of photons.
Now, the reason I'm doing this is because I would love to know the V of my freed electron. And of course, I need to change this into joules. So my V will be twice 0.907 times E over mass of electron square root. Yeah, because of this formula. What was the formula? HF equals KE plus work function. So this was 1.907 electron volts, and this was 1 electron volt. So this must be 0.907 electron volts.
We have to turn it into good answers in electron.
Oh yes, definitely could be something you asked to do.
Not
Yeah.
like all the time.
Not all the time, no, just as a possibility. It's quite usual.
If you don't mention it.
Then it doesn't matter. It doesn't matter. 5, 6, 4, 8, 4, 5 meters per second. Now, how can knowing this give me the current? Well, this is the way I'm thinking about it. When the electron is freed and then travels in the conductor, it has a small charge. How much charge? Well, each electron will have a charge of E. So the question is, in 1 second, how many electrons are released? Let's see. We got it
So 3 point.
this many. So actually, I suppose, I'm sorry, I didn't really need to know the V, because I actually know how many electrons are released in a second. And current, if you remember current, it's charge per time. If the time is 1, then in this case it's just a charge. And it'll be the number of freed electrons times the current. Sorry, the charge of the electron. That's how much I have released per second.
Okay.
Yeah?
That's a lot of energy.
Well,
Lot of current.
well, you don't know. Let's see, 3.9, 3
Oh.
point.
Okay, no, never mind.
Yeah, we didn't discover the secret to unlimited green energy with our photocell and stevinium. Times 10 power 18.
Could be 0 point.
Let me just put a note here. Sorry, didn't need, I think. That is a 0.629 amps. So that's how much current I get in my little photocell. Yeah. I think I would need to know this to work out the voltage, possibly.
Speed? What of the voltage?
But possibly, because I only know the current, I don't know the voltage. No, I don't even think I need to know
How would the
this.
speed gauge the voltage?
I would have thought the kinetic energy of the electrons would be important. But maybe not. Do I even need to know the speed?
No, but there's
Do
something.
you know what? You know what? No. This is the speed of when the electron is released from the plate, but when it enters the metal conductor, well, I'd imagine it'd be going much less when it enters the conductor. Yeah. So actually, no, forget about that. Yeah. We can just jump straight to here. So there you go. That's the current here that you get from our little solar panels. All right. Well, we have a look at the quantum one now. We have quantum worksheet to do. I've done half of the physics. Nope, did not.
About the math.
I haven't. You haven't even opened them.
Yours is not important.
I'll correct yours first.
You forgot the references.
Why am I so nice to you? I don't know. I feel sad for you. Because all these boys pick on you. Because they're jealous of you.
Because you're getting it.
I believe in you.
But getting it here would be fun.
Note to self, give Yahya a C.
Between 42% for you.
Yeah, no, I have a couple of ones to remember now.
You can forget mine.
Okay.
Did I open this, or I'll give it 5 seconds, and if it's not starting to open, I'll pick it again. 5, 4, 3, 2, 1. Okay, I got that. Are you showing them your dirty lattes again?
I showed them the Flat Earth Society has
Oh, yeah.
all around the globe.
It's the comment that takes me off, yeah. That's
I
what
didn't
get.
notice it.
Slowly.
I didn't notice it. I was like, okay, slowly, what's wrong? Flat Earth. All around. I'll send the box card.
Right, let's have a look at this one.
You know, I saw a car, like, when I went to Dubai for that 1 week.
Wait, they have cars in Dubai?
The rim?
Dude, I thought it was just camels. You have
Yeah.
cars, congrats.
No, when they ride the scooter, they call them cars.
Dude, like, that's so sweet, isn't it? And is it the scooters you have to kick with your foot?
No, they have small mattresses on the side.
2 million euro scooters.
The rim?
Nice.
One car moved, the rim,
Oh yeah.
What? It was like this huge Hummer truck.
Hover truck.
Hummer car.
Oh yes, the big SUV, the big the
Yeah.
big Hummers. What are they called? Who makes them?
Americans.
I know, of course, American. What car company? Is that the name of the company or the name of the model of the car?
Hummer is a company.
No, it's like Infinity belongs to Nissan and those kind of
Yeah.
belongs to Ford.
It was like completely customized, and the rims, they don't spin when the car moves.
You know the price of these rims or price of the car?
So it's not
It looks like it's literally levitating. It's just.
that is kind of cool.
The
Alright.
The price of these.
I was so like.
It's the price of like 5 coins.
I wonder how they do that. I'd imagine if you put,
Oh no, it's
you would need, you would at least need the hubcaps not to be balanced, to have a huge weight at the bottom, so they're always trying to hang down.
Yeah.
But the
Yeah.
wheel will constantly want to try and turn it, so you would need something else to stop it from turning.
No, it does move, but like slightly. It's like
Yeah.
It's like
No, not even one. It doesn't even like twitch.
Send me the video. I'll have to do some
No, this
physics
I saw
on
it
it.
in real life. Like I didn't.
Ah.
Andrew, next time, capture.
I'll get
Sorry,
you a video.
pictures or it didn't happen, okay?
Video, not
Video or it
picture.
didn't happen,
But it
fine.
looks like it's
I
levitating.
can find the video now. So.
No, that's alright. The lowest energy an electron can have
If you
when...
come for my ride.
Exactly, yeah.
Yeah, I'm gonna add those hubcaps to my scooter. Alright. Like, the lowest energy an electron can have when orbiting a proton is minus 13.6 electron volts.
And then more implications to do that.
This the second energy level is minus 3.4 electron volts. How much energy is lost if an electron falls from 2 to 1? So if it falls from 2 to 1, how much energy is lost? The lost energy will be the difference between the two.
10.2.
Now you can think about it as a net, yeah, you got 10.2. Because I said the word lost, I don't put the minus in here, because I know it's a decrease. Yeah. In order to keep the energy conserved, the electron will emit a photon. What is the frequency of this? Well, you have HF is equal to this 10.2 eV. So the frequency here will be 10.2 E over H. Thank you, guys. Thank you, girl.
2.47.
What is it?
2.47 times 10 to the power 15.
Thank you. C. No, sorry, that was A part 2. Now on to B part 1. While in energy state 2, a photon is fired at the electron, and the electron just about reaches energy state 3, which is minus 1.51 electron volts. What is the frequency required of the photon to do this? So it needs to go from, what did I say? 2 to 3, is it? Yes, so to go from energy state 2 to 3 means you need to go from minus 3.4 electron volts up to minus 1.5 electron volts. So how much energy is 1.89 electron volts required? So once again we can have HF is equal to that. So F is equal to 1.89 E over H. Which comes out at 4.57 times 10 to the 14 hertz. And while in energy state 3, a photon is fired at the electron, and the electron is freed. How much energy is required to free the electron? So finally, while the electron is in energy state 3, level 3, what is the energy required of the photon to free it?
4 point. No.
What is it?
1.89.
No,
4.57
that's the frequency. At times, yeah. Which will not surprise you to learn, it will be 1.51 electron volts. Why?
I said,
No, you didn't. You said, you were talking about this, weren't you? You
No.
said 4.57.
I said this, but then I said 1.5.
Did you? Oh, I didn't hear that. Why? Yeah. Tom, Faisal.
That is the energy of that level.
Yeah, that would be good to know before asking that. How much energy does the photon need to free the electron trapped in energy
How do
level
you
3?
teach it?
Yes, a good question. Maybe I don't teach them. Maybe I think I'm teaching them, but nothing's going in. Here, 1. This is the energy while in level 3. The negative means it's trapped. That's the energy required to actually free it.
Why is it not negative?
Why is what not negative? This is positive.
Yeah, well,
Because the
why-
photon needs this energy to cancel this energy. What's
so
wrong,
we're
Andrew?
trying to make it 3 to 0.
Doesn't
Yeah.
come out as 1.51.
Did you don't forget, I did convert it.
0.829.
Wait, no, this was the energy to move it up from 2 to 3, not to free it.
Okay.
Yeah, so it's not using this one.
And technically the answer is given in the question.
Yep, and that has happened in the exam. Again, that's why I've asked it.
But like,
For like 1 mark.
So you're gonna have to show any of the things right now.
This would be like a 1 mark question in the exam, so you just write the answer.
yeah, and they're giving you the energy required to remove
Can I
things
continue?
from the last one, unless it's something like this. Yeah, they won't give you the energy needed to move from 1 to 2 and then leave that way and then they
Awesome.
ask you without giving you the paper.
What's up, Andrew? Got a question?
Just asking, like, how do we know if this E3 is the last energy level?
Oh no, it's not the last energy level. But it doesn't matter if it's the first or the last.
Yes. Okay, I see it now.
Yes?
I
Okay.
see it.
Let's see the next one. Number 2. An electron is accelerated through a potential difference of 10 kilovolts. It strikes tungsten with a work function of that. What is the wavelength of the photon emitted from the tungsten? So let me just draw what's happening here. You have some kind of electric field. An electron enters the electric field. The electric field is at 10 kilovolts, so it's a huge electric field. What happens when the electron enters the field? It will accelerate and fire out the back side of the field. You have a couple of formulas here. Remember, electric field strength is voltage over distance. Force is QE. And also, what is important for right now is potential energy is QED, or also QV if we start at the start of the field and end at the end of the field. But in this picture, the potential energy when it enters the field will equal the kinetic energy when it exits the field. So in this way, we can get the velocity of the exiting electron. A half mv squared equals QV. So V, velocity, 2q voltage over mass of electron square root. Let's calculate that. 2 times charge of electron times 10,000 over mass of electron. This should be pretty fast, and it is. 5,930,9698 meters per second. Now what happens in the story? When the electron leaves the field, it hits some tungsten. When it hits the tungsten, a photon is released. By using our formula, HF equals Ke plus the work function, we can get the photon's frequency. Yep.
One question. What's the V over here?
Which one, the left or the right?
Right.
Voltage V.
Okay. That's
Yeah. Okay. So F equals Ke plus work function over H. But I don't want F. I actually think I want lambda, do I? Yeah, I want lambda. So F is C over lambda equals Ke plus work function over H. So finally, if I squeeze to the left here, I'll zoom out just. So that means we can get wavelength will equal H over Ke plus work function. Times C. Do you know what, guys? I just realized something. Again, I didn't actually need this. Because, no, I don't, because here I need the kinetic energy, which I can say is just equal to the potential energy. Ah, yes, now it becomes clear. So that's the same as H over PE plus the work function. See. But this is the first year I've realized it. And it is, yeah.
Ah, this is why they were failing.
Yes. That and the chronic lack of revision as well. I wonder which one mattered more. Right, let's calculate this. Oh yeah, and of course, what is the formula for potential energy? QV. And what's the work function, did I say? 7.2 times 10 to the minus 19. You get a tiny wavelength, 0.124 nanometers. Goodness, that's tiny. And so that tiny wavelength. Last question. What part of the spectrum do you think it is?
Show us the wavelength.
Not even a nanometer.
This is visible, it's not visible.
Oh, it's not visible, because visible ends at like 450 nanometers. So you need to think after visible, and much less than ultraviolet, because ultraviolet's like, I don't know, 250 or something. X-ray, yeah. Yeah, this is an X-ray.
Visible and
I think it's about 450 or something like that.
as in
You can't see it anymore.
less than that.
Less than that, yeah.
No.
350 was it?
Isn't this to the left of the spectrum? 0.
Do I have it backwards? Sorry. Small wavelength. Oh, it's on the other side, isn't it?
Yeah.
Sorry. Yeah, so not X-ray then in that case. Yeah, what would it be then on the other side?
Microwave?
Yeah.
Because 0.1.
No, I think it's smaller than. I think.
Gamma.
No, you gotta be thinking if it's on the other side, small wavelength.
TV?
Wait, no, hang on. No, I was right the first time. Juan was right the first time as well. Small wavelength means high frequency. It's on the other side of the spectrum.
Yeah.
Yeah, so it is X-ray.
X-ray or gamma.
X-ray or gamma, yeah. So, congratulations, you've made an X-ray machine. This is what they do at the hospital.
Wait, how do we know what it's X-ray?
You have to learn the spectrum.
Wow.
You can actually make this at home, if you would like. Yeah. It's very, very simple. This is how you make it. Can I scroll down? Or right here? Right, step one. You need a power supply, obviously. So, for example, and it needs to be DC. Okay, so you have some DC power supply. If you use your home voltage, that's AC. So you would need something to convert to DC. You can buy these in a hardware store, maybe €30, no big deal. So you convert that to 220 volt DC. Now, how much voltage do we need? 10,000. How can we increase the voltage?
Transformer.
That's right, so we step that baby up to 10,000 volts. Yeah. Then we need 2 copper plates. Again, go to your local hardware store and find 2 copper plates. Drill 2 little holes in them. And if possible, if you could put this inside some kind of vacuum, that would be difficult. It's not necessary. You could probably get a vacuum tube out of an old TV or something. Yes? Now, you'll need a piece of metal here that gets really hot, and you're trying to get some of the electrons to hop off the metal and travel into the hole. Connect this up to your large voltage, and the electron will fire through. Then, on the other side, you have some tungsten. Put it at 45 degrees. So, here's the electron coming out, and you put your tungsten propped at 45 degrees. So the electron hits it, and the photon is released. Then simply stand here in front of the X-ray and put a giant photographic plate behind you, something you would find in an old camera. The older the camera, the better. This should be done in a dark room or the photographic plate will be destroyed. Then, after a few seconds of slowly exposing yourself to X-rays, you develop the film and discover your bones. Yes. You too can make an X-ray machine at home. Yes.
This does not get you one more subscriber.
Oh, I should rename the video. Yes. Okay, so I guess we didn't quite have time to look at the maths, but we are now totally finished with physics. We'll look at the maths and then start, I guess, maths or physics revision first. What did we say we want to start with?
Physics is on Monday.
You're going to give us physics test
It's-
this week, so.
No, I'm going to let you choose during the test which of the 2 papers you want to sit. But wait, is physics the first one?
Yeah.
Then we should do the physics first. We should have slightly more physics this week, 2 more hours maybe, because we can always do an extra maths on that day off next week. Yeah, unless you really want to do extra maths this week.
No, I think physics is...
We'll start the physics then? Okay. We'll look at the most recent paper on Moodle. I think there might be an exemplar on Moodle. We'll start going through that then as revision.
You don't get any things as a teacher that we can access?
You mean like heads up, I know some stuff on the exam that you don't type of thing?
As an exemplar.
For the is coming year? No. I only have an exemplar, like historic exemplar.